Okay, hi everyone, and welcome to this Twitch session where we're going to talk about everything that has been done since version 11 in the domain of natural language processing. So everything that is new in 12, and by new in 12 means, everything since version 11. So 11.1, 11.2, 11.3. We'll talk a little bit more about what's more, the most recent thing, of course, because it's always the most exciting. But it will include all that things. And there's been a lot of things for natural language processing. Mainly, it's bigger integration of deep learning capabilities. So both for applications. So basically, I'm going to talk about applications that basically we did with our tools, and I'm going to talk a little bit about tools as well. So that you can create natural language processing applications. And it's mostly oriented towards the machine learning approach to do natural language processing, and notably the deep learning approach to do natural language processing. So to summarize, what are the big new things? Okay, in 11.1, there was the we added the recurrent layers to the neural network framework. So this was a very important thing, because before you couldn't handle sequences with a neural network framework, and now you have things like long short-term memory layer, or even basic recurrent layer, or gated recurrent layer, that are typical layers that can handle sequence as input. So it's recurrent, but the way you use it is a bit like a forward layer. It's just that you have a sequence as input, and it output a sequence. That's just what it means. And why is it recurrent? Is because it actually reads the sequence step by step, and keeping a memory while reading this sequence step by step. So the way that's why they're called recurrent layers. The way they process is that they read from left to right, and or from right to left. Actually, you could have actually there's a net bidirectional operator, which is one way to create a network. So one recurrent that will read from left to right and create basically output a sequence. So it takes a sequence as input, it output a sequence, and then the backward one will read this output sequence and output another output sequence. So it's kind of a two-layer, which is useful. It's a very useful operator that also been added. Let's see when actually. This one has been added probably even more recently, 11.3. Okay. Actually, it's still about tools, and I guess I'll show example later. You can create custom recurrent layer. So using, for example, the net fold operator. So here is, so I showed you long short-term memory, basic recurrent, gated recurrent layer. This is kind of, built-in recurrent layers. But if you want to do a custom, you can also do that through net fold operator. So operator means that it takes a network as argument and outputs another network. For example, this is a simple, what is this? This is a simple recurrent layer that just sums everything. So, it takes, okay, this will be the one that sums everything. So the graph, we do a graph that has two inputs, an input and what we call the state, and it will just sum. Okay, so very, very simple network. And if you put it in a net fold operator, then we can do it. So let's just try it. Okay, it does a sum, great. Now I put in net fold operator, and this will basically connect the output to the state. All right, so it's kind of that's the recurrence that is done. And if I apply fold here, you will see that and of course at each step it outputs the output. Okay, so it's kind of, it duplicates. So there's one of the output that goes outside, and another output that is looped back to the state. All right, and that's why 1, 2 is unchanged, and then at the second vector here, it will be the sum of the first vector and the second vector, and third position, it will be the sum of all these vectors, and so on. So it's just sums, and it's you guess that with the name. It's very similar to what the fold operation is doing. So really, the fold operation is kind of a basic recurrence that it kind of maps over this, but keep a memory of the computation and use it for the next computation, which is actually nice to see all the like the functional framework adapt quite well to neural network framework, and we're pretty pleased with these operators. There's others such as nest operator, net map operator, net map thread operator, which are very useful as well. So anyway, that was one big thing. Then the other big thing is all the net models we added for natural language. So some of the these net models are so for natural language processing. So some are, let's say, word embedding. So Glove is a classic word embedding. This one, okay, 100-dimensional word vectors trained on tweets. So what this is, by the way, I give kind of an overview, and then we'll go into examples, maybe one by one later. So, okay, so this is downloading from the repository. It's going to take a bit of time, 1 minute. But basically what this is just a big table. And for each word, it has a vector that is associated. So, okay, let's wait 30 seconds more. But let's say if we give car to this network, it should give a numeric vector of size 100, as the name indicates. And there's many other. Let's go to the repository. Neural network repository. Wolfram. Should find it. Okay. And so let's see, there's a bunch of Glove, for example. Okay. 100, so it could be a vector of size 100, 200, 300, and so on, 50, and trained on various data set. So this one has been trained on tweets, but some have been trained on common crawl, 42 billion words, I guess this means. Some, oh wow, this has been trained on big common crawl. All right, so you can see this is an embedding layer, so it embeds classes or categorical variable. In that case, it's words, and it's just a big array. Huh? So you have 1 million possible word as input, and it outputs something of dimension 100. So let's see car, and it should. I don't know why it takes some time. It should not. It should be actually extremely fast. It's just a lookup. Maybe it needed to initialize itself. Okay. I guess it's initialized now. It's in memory. So you see that's the vector for car. And that's a vector that captures a lot of what car actually is, right? A lot of semantics. So you probably know it's not human language. It's a numeric language, but you can see that as one of them tell that it's a, that it's a vehicle. Another thing tell that it's, I don't know, human-made thing, another thing. So it is sort of maybe something will tell that it's typically a noun, and so it's not interpretable, but that's the idea. That's kind of features of what the word car is, and this is extremely useful to start basically any natural language processing application with a neural network. The first thing you would do is always to extract vectors from words. So you never start, because there's already a lot of knowledge there. So if you start from scratch and you try to train a recurrent network, let's say for, I don't know, what task could it be? To find entities in a text, or summarize text, or things like that. If you start from scratch, like just reading character one by one, and you will need a lot of data to make something work. Whereas if you start by pre-processing the data into these vectors, you would need less data because there's already knowledge there. It's called knowledge transfer. So anyway, we have a bunch of these. And so there's also, let me start to do section. So there will be new recurrent layers. Other things are the net model. So let's say this is a word vector. So classic word vectors, I will say, because there's another type that we'll talk right after. Let's put that there. And so this was basically how every NLP task was done in the last few years until this year, basically, because something better appeared, which are the word vector in context. So word vector in context. So it's new models that instead of, so okay, if I give to this net model, if I give, you know, let's say the red car, and if I say, let's say, I don't know, his name was car, which actually doesn't make sense really, but anyway. Then car, so let's grab the last one, 4. And I will do the same here. So I want the word vector, so it's going to be 3. I want the word vector for cars. You see, it's the exact same thing. So what it really is doing is just extracting the words and extracting their vectors independently. But really, in some cases, because of the context, it's changing the meaning of the words. So now we have model, and the most famous is probably BERT that we have. It's made by Google. By the way, this whole idea kind of started a model we don't have yet. It started with Elmfit, which was, I think, a classic recurrent network, train a lot of data, and basically use the output of this recurrent network to have your word vector in context. And then there's been a craziness because it's so effective that many groups try to do better word vector in context, and that was Google's version, which is very good, which all use transformers. We're going to talk about it after. So here, if I do the same thing, there's a red car, and I'm not sure there's going to be, I think there's an input and output. So let's see the length of this business. Okay, 5. Okay, so it's like the 3 word, but also input output. So if I say number 4, it's going to be the vector for car. And let's just take the beginning. Okay, it's the beginning of and if I say this one, you will see that it's a different. So this should be the 5th. It's going to be a different vector, which has some similarities, right? Like these two, actually, you can see that it's some, I guess, I don't know. Yeah, I guess statistically it's a little bit similar, but they have differences because of the context. And this, nowadays, for many natural language processing applications, almost all of them, the best performance are when you first pre-process the data with such word vector in context network. And in particular, BERT is pretty powerful. Okay, so that's another big thing that we have in this version, and then it's all the applications that basically we did using, you know, the fact that now we have powerful word vector in context, and that we have recurrent layers, and that we have transformers as well. So that's another thing that I will talk after. This is a new architecture. I mean, new. It has 3 years now. It's not a recurrent layer. It's not a convolution layer. Something else that is attention, and that is very, very good for text. So I'll talk a little bit about that. And then we also have applications that we use basically using transformer, the word vector, recurrent layers, and so on. And we did cool application. And I'm going to talk more about that. Actually, now let's dive into the examples. I'm going to check if there's any question. By the way, don't hesitate to ask questions. I'll be happy to answer them while talking, while giving this presentation. All right, so now let's dive a little bit into the examples, and we first start with applications. Okay, so first one, general knowledge question. Okay, that's just one example, which really using a combination of factual answer and Wikipedia search. So, I mean, the application is really find textual answer. I mean, the function is find, the main function is find textual answer. So find textual answer is the idea is that you give it a paragraph. Oops, sorry, what did I do? You give it a paragraph, like Paris is the capital, you know, and most popular city of France, blah, 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 blah. And then you ask a question about this paragraph. I mean, in that case, just a sentence, right? In natural language as well. And it will figure out, so there's a neural network that does this job, what is the answer? And that's pretty cool. It's unfortunately, it's not yet to the level of human performance, even though some benchmark make you think it is. This function has been mainly done, not only, but mainly done with the Squad dataset, which is like a dataset made by Stanford, which stands for Stanford Question, exactly, the Stanford Question Answering dataset. And since dataset appeared, there's been many groups, labs, and so on, and companies trying to do the best network. I must say that currently our network is not like because it used to be the state of the art, but because things are going so fast, it's not state of the art anymore, which we're going to improve soon. So actually, that's funny. Now the best performance is beating the human performance, but this shows when you see something like that, it's often the sign that the data set, like it's easier than you think for a computer to solve this problem. Like there's some tricks that doesn't rely on actually really understanding the text. And also for this thing, often humans, you know, like it's a bit boring to answer thousands and thousands of questions. So you do mistakes because you don't necessarily pay attention. So I don't think this number should be taken as, okay, now the machine is better than humans to understand text. I think it's very wrong. The machine is still way worse than human to understand text. So hopefully we'll have harder data sets soon. So the competition might still go on and we might progress science. Anyway, so the example here is how we're going to combine factual answer and Wikipedia search to do a general open domain question answering. So let's see. So, okay, let's say that was the question. And oops, let's copy this. Copy, yeah. And we want to do that without a paragraph. So basically find a paragraph from the web. So what we're doing is we're grabbing all the articles that speaks about Sagrada Familia by using Wikipedia search. And we have a bunch of articles. And then we find the content of the articles, right? We extract the text. And then very simply, we use find textual answer on all these contents, which actually are a lot. So scale is going to be slow because it's quite of a big network. And it seems quite a lot of content. Let's see. So, okay, that will be the first Wikipedia page. Oh, that's big. That's big. This is going to, okay, I hope it's not going to be too long. Find textual answer on this. bet it's going to take a long time. Okay, and here basically we do that by locating answer and selecting. Okay, great, and it found the question. So we kind of created a general knowledge question answering system that just query the web, I mean Wikipedia, and answers questions. And this is to see the alternate answers. Actually, maybe we just, I don't know how long it's going to take. Oh, no, good. Good. So let's do the grid. See if, oh, no. Oh, no. I have to do it again now. Oh, I didn't copy. Okay. It's actually faster than I thought. I forgot what trick we used to make it that fast. Because there's like many articles. It's like 50 articles. Okay. Anyway, all right, let's do the grid so you can see that Gaudi was kind of the clear winner, which actually makes me think that we could improve. You could start with the example and improve it by grabbing the kind of second guess, because clearly it's 3 times the same. So the score should be kind of average. All right, okay, because then something I should have said is that find textual answer is not just, I mean, it's a bit simpler than answering the question. It is actually finding in the text where the answer is. So what it did here is that it found that here there is the answer, and it found that with this score, and that here in one of the article there is another answer and another answer. So you could actually combine these answers, and you'll have to combine the score in a smart way and do a better general knowledge question answering. And then you can compare it to Wolfram Alpha and see, if it's better or not. Let's see Wolfram Alpha, what it does. It should be a Wolfram Alpha is better, so. But who knows? Sagrada Familia architect. Actually, I mean, it was better and less good, because probably they all worked on Sagrada Familia, but clearly the important one is Gaudi. So Wolfram Alpha used a curated database, and so it kind of like all of these architects I've listed have been worked on Sagrada Familia. Nevertheless, Gaudi is placed first. Yeah, timeline. Okay, cool. So that was find textual answer. That I hope we should make it much better soon, but it's already fun to play with. The other one is text cases, and that's the most important application. That's my favorite application. And basically, these 3 examples are about text cases. So let's see the first one. So the idea of text cases is to do a very, very generic, a very wide named entity recognizer. So let's see. I'm going to graph the Wikipedia page for the moon. Okay, this is a snippet of it. And actually, we could see all of it. Like that's a Wikipedia page for the moon, right? And we're going to ask text cases or text content. It's basically the same function. Text content is a bit like, tell me, like grab relevant entity from the text. And let's run it on the moon. And okay, you're a bit spoiled here. That's what it should be, unless it's broken on my Mathematica. 4 seconds remaining. And it should give that as a data set, like here. Okay, as interpreting result. Might take time. Okay, let me comment on what should happen, and then we'll confirm. So what it should happen is that it will find things like planetary moon, planet, star, quantity. So you see that it also has a classic entity such as city and country and things like that. But we went much further. Actually, if I go on a text content page, I could say see the list of the content type. So what text cases and text content attempt to find, because they're not perfect. So you have classic structural element, like find all the words, find all the sentence, all right. You have all the grammatical things, like noun, verb, okay, noun phrase, things like that. But then you have things like find everything that's a positive sentiment, or find all the profanity. And or find all the thing in English. That's something you can do as well, that I think we forgot to write here. I think that's a useful thing. Or find all the snippets in Spanish. That's things you can ask. Quantitative element you can do. Date, location. Location is a cool one. We'll show an example of that. It's like everything that can be pinpointed on the globe. Email address and entity type. And you can see there's many of them. It's like you could ask all the reef in the text, all the comet, all the famous gem, all the ships, which is definitely not typical of entity recognizer that are usually restricted to maybe 6 entities. You can also ask specific entity, like find all the mention of New York City. All right, of course, it is experimental. We're going to try to improve. Like many of these are not working that well. So we're going to try to improve that, but at least that's we have a big yeah, we hope to have a big objective there to have even more, actually, which we're trying to work to have even more type. Okay, so that's the result. So you can see, okay, it found that it's moon. Okay, that's a confidence probability, the position in the text. Okay, now that it's type and then it's interpretation, right, as an entity. And so text cases is basically the same thing, but you can do it like this. Text cases of moon. And then I can say, I want all the planets, right? And it should find all the planet. Apparently, okay, the detecting entity is fast. What takes time then to try to interpret with our entity system all the results. Okay, you go. Because I didn't do the interpretation, it was pretty fast. So here are all the mention of planets. And then I can also do, as we're doing, I can also do, I want specifically the mention of Mars. And hopefully interpret the planet. Yeah, so this will end. Let's see the highlighted snippet, huh? Otherwise, we won't know if it was a good Mars or not. Highlighted snippet. Did I write that down correctly? Should tell me something if not. Can also find topics. Oh yes, and languages, yes. So you can say all the, all the thing in Italian, all the thing in Greek, and it should find it. Okay, you go. Mars size body called Thea, Mars size body, okay. Mars and Vesta, present day Mars, okay. Makes sense. Actually, I'm surprised. Okay, let's do a test. Let's do a test. Maybe it will work, maybe it will not work. But if I say I ate a Mars bar, I hope that Mars is not going to be selected. But maybe it will. No, great. And I went to Mars in my spaceship. Here you go. So yeah, it's not only using the spelling of stuff, it's using the context. And that's a neural network that you can see. I'm not sure we have I mean, it's in the repository. I should figure out what this network is. We have it in the repository, but I'm not sure it's kind of an official one because we use some anyway custom things. Maybe I'll try to find it after. It's a cool network. Okay, programming language also you can extract. So yeah, text cases. That's my favorite function. Favorite NLP function. Okay, location. Let's do this example. It's pretty cool. We get text about rice. Okay, so that's text about rice, right, from Wikipedia. And let's find all the location. And let's interpret them. So location entity. So we're going to have the entity as an output. Hopefully the interpretation will be not too big, not too long. All right. Yeah, we try to put an effort because this function is so slow. Try to put an effort in giving kind of a monitoring of what's going on and predicting how long it's going to take. Okay, so now I have a bunch of locations. So it should give me entities that can be put on a map. So Asia can be put on a map, or United States, or Italy can be put on a map. Or even some, okay, it's a bit everything, right? You have some administrative region, you have some, even, some museum. Oh, this is a group of museums of the Far East, but they can be put on a map. So we grab them. So it's a bit of okay, I mean, a lot of regions. University of Cambridge can be put on a map as well. So it has been extracted by this location thing. And of course, what we can do is, so here we count them. So bigger will be the region that are mentioned more into the text. So you can see this is probably Asia in the middle. We should put a tooltip to know what they are. I wonder if we can do that easily. Here you have the number, but I would like to put, how can we put a tooltip? Yeah. Hope it's labeling and legending. Let's do this. Here you go. What is that? Oh, I have to do labeled. Okay. Well, maybe we don't have time for that. Or do we? If I do normal, and if I go, okay, labeled, and I'm going to label by map that, and this is going to be unchanged, and the label is just the first argument, right? Up, and this should work. There you go. Okay, well, it makes it a little bit more useful. So anyway, that's an example. Find dates in text. Okay, let's not do this one, but basically find all the date. Here you use a timeline plot. So it's taking the word war, Wikipedia data, find all the dates, and put them in a time plot. And as you can expect, you have things for main wars. I mean, the 2-word war, and kind of this, I guess, was the, what was that? Another French-German war. It was more in 1870. No, we could look there. You could look. Anyway, and just grab the snippets so you can have an idea. Can be a nice way actually to summarize, understanding main conflict by very quickly analyzing the Wikipedia page, doing the pipeline, and having the snippet. And here you go. In 2 minutes, you can have a little history lesson without having to read the whole Wikipedia page. So hopefully this is the sort of thing that can be useful, not just for history, but analyzing, I don't know, many papers of biology and having a program that kind of identify what you need and give you a small snippet and you know, things like that. That's one of the goals of this natural language processing functions. There are many others. I think it's really a Swiss Army knife, these text cases. So many applications actually boil down to text cases. So yeah. Okay, so that's let's finish for text cases. And let's continue with the other example. That's exactly what I was mentioning about the word in context. Okay, that's applications up. Bye-bye. Let's go to the word vector in context. And this one used Elmo. So that's older. So it's before BERT. I think it's the first that was bidirectional. So the unfit that I tell you about reads text left to right, and it has been trained to basically predict the next word. It's a language model, and this one hasn't been trained to produce the next word. It's bidirectional, and like BERT actually, and this allowed to have a little bit better result. The problem is that you cannot use this bidirectional to, let's say, create a language model. You cannot use as a feature extractor for a language model, which you can do with unidirectional. And actually, I'm going to talk about that with when talking about the transformer. Anyway, that's Elmo. We can have a look at it. It's great. Let's up this a little bit of surgery. What's happening? Okay, Elmo produced 3 vectors by default. So 1 vector that is not contextual and 2 that are contextual. And this is a little surgery to make the Elmo now return 1 vector. So if I say Elmo car, I should have just 1 vector. Great. Yep, yeah, just 1 vector. Okay, so, okay, well, here was the example. Actually, I think this was old. Now it doesn't return. This was probably in our development version. Yeah, it doesn't return numeric array anymore. Okay, and now we're going to have fun with several sentences that talks about Apple, but in different contexts. Sometimes it's apple pie, sometimes it's Apple make laptops. And so sometimes it's a fruit, sometimes it's a company. And what we're doing is that we are preprocessing all these sentences with Elmo, and then we are visualizing them in the feature space. And you can see that thanks to this Elmo extractor, all the company are together and all the fruits are together. Actually, what we should do instead, okay, this was a whole sentence. All right. But what we should do instead is grabbing the vector only for the word. And I think that's what's happening right after. So is it? Yeah. Let's see. So, okay, this is a dimension reducer that's, okay. This basically learned to reduce the dimension of the vector that was of dimension, what was dimension? 1024 to dimension 3. And this is a net that's going to, okay, what's going on? Hope there's no problem in the version I'm using. Apply the reducer and then colorize. Okay, so the idea is to visualize the word vector, but we cannot visualize this vector because they have size 1024. So instead, we reduce the dimension to 3, and then we convert them into a color. And that's we can kind of visualize the word vector for each of the words. So for example, the cat is on the mat. This is the color for this is the color for cat, all right? And so on. And now we do that for all our sentence. And normally we should see that all the apples depend on the context. So yeah, this one is pink, Apple makes laptop, but this one is sort of yellow-orange. And yeah, these three are similar color, and these three are similar color because they actually mean Apple the company. So that's a pretty cool way. It's not me that did this example, as you can notice. And it's a pretty cool way to visualize. So yeah, it's someone in our team. The word vectors. Okay, let's continue. We still have 20 minutes. That's okay. That's one net model about clinical concept. Okay, so basically this is an embedding layer as well. So it's the same thing as the embedding layers that I was talking about before, like the same thing as the word vector, the classic word vector that I was talking about before. But this time it has been specifically trained for clinical concept. Let's see if we can play a little bit with it. So let's call it clinical. I mean, okay, let's put that in the classic word vector, huh? Classic word vectors. All right. So that's a network. And it has been trained on clinical concept, unique identifiers. Okay, so it's not super interpretable, but this is a concept. This is a word, you can see in a way. And this is a vector associated to this word. But then we can do things with that. So, okay, let's grab clinical data from the data repository. So here now we have the ID, right? The unique identifier for each concept, and actually their human name, what type they are, and okay, where it comes from. And what we do here that we select all things that have in their name virus. Okay, so it should be all the viruses. And okay, let's grab the ID of the viruses, and let's do the same for bacteria. Okay, let's see a few bacteria. I mean, okay, that's few bacteria. Doesn't tell you much, but anyway. And now we do the same thing. We pre-process all these viruses and those bacteria by the network, by the embedding layer, and we visualize this in the feature space, knowing that we forgot, like there's no tag here. And okay, yeah, and so you can see that the bacteria and virus are actually separated, kind of. Some are a little bit outlier. But it's important to know that we didn't include the fact that there were virus or bacteria to feature space plot, except for labeling purpose. So by itself, it figured out how to distinguish these two things, even though it doesn't know which one is which one. All right, that's one way to visualize this. And I guess you could do a lot of things. You could do a search system that is based not on the name. So, if I type virus, I have all the virus. But now I want all the virus that are like African horse sickness virus. We could, you know what, let's do it. How could we do that? Well, maybe it's going to take a bit too much time, huh? 15 minutes left. So we could just use nearest and basically pre-process all this concept to their features, or use feature nearest directly. We could use feature nearest directly. And with that, we'll have a sort of search engine for clinical concept. If I type, that would be great not to have typed the identifier. If I type African horse sickness virus, then it will give me everything that is close to. Okay, that's how you can use these net models. Okay, that's an example about enhancing the sentiment analyzing using transfer learning. So basically, that's what I described before, is that you get this embedding, right? These word vectors. You create a network. So this is okay, only one layer of long short-term memory. And so this is creating a classifier, all right? This is a classifier that will class positive or negative. So what it does, okay, that's always interesting to look a bit at the networks. Let's see. up. Let's call it recurrent. Oh, let's go back to the top. We already started. Okay, recurrent layer. Okay, that's an example of a net chain using plus an embedding. So you have the embedding. So you see this creates a bunch of vectors, like the cat is on the mat. We create a bunch of vectors, one for each word. So it's a sequence, of course, because the sentence can be shorter or longer. So we don't know how many vectors there are, but that's okay. So this first, okay, embeds the sentence, and then it applies this long short-term memory that basically takes a sentence, takes a sequence as input and output a sequence. And then we use sequence last layer, which is basically use the last vector. Okay, so it outputs a sequence of vectors, and then you just grab the last vector, and then a linear layer on this last vector, a softmax, because we want to convert that to probabilities, and then a decoder that tells that the two classes are positive and negative. We don't have to put the dimensions because, because of the decoder, we know the final dimension of the linear layer and the softmax layer, like all of that is automatically done by the framework. Yeah, that's kind of the, simplest way to do like it's really a vanilla recurrent neural network. And actually, before going to anything more complicated, on basically anytime you want to use a neural network to classify text, you should do this basically. And then you can go to more complicated things, but and often it will have very good performance. So okay, and I'm not sure we'll have time to train that, but okay, it's a data set where you have a paragraph, and if this paragraph is positive or negative, and then we're going to train that. And this is freezing. Okay, interesting here. You see, we are freezing this embedding. We don't want to relearn this embedding. And that's important if you don't have enough data. If you have a lot of data, you can let everything free to learn. But if you don't have much data, you will get worse results if you also learn this embedding layer. So the best is to freeze it and only learn the few parameters. I mean, few, there's still a bunch. Actually, might be written somewhere. No. And this is called, transfer learning. This whole business is that we transfer the knowledge that are in this embedding, in these embeddings for our task. And all right, the arrow is going down. I don't have much time, so I'm going to stop it. And okay, and then we can try it for fun. This movie is one of the worst I ever seen. I really hope. Oh, I have to grab the net first. Train net, training results. Okay, that's our train net, right? Short-term memory, blah blah blah. And it's negative. Great. And because there's an encoder, we can also ask for probabilities. Okay, so it's somewhat, I like when networks are not too confident, it's when they're too confident that there's something wrong. So it thinks it's somewhat negative, but it's not completely sure. And oh yeah, they do the classifier measurements. That's basically going to take test sets, so something that has not been used to train, compute the accuracy, and give it, oh, we're actually not that far from this one. Surprised, because we stopped rather early. Oh, also a nice feature is computer certainty that gives an around object. So, because a test set is a finite size, you always have a small statistical error on your on your accuracy. I think it's good to see that if you were using a bigger test set, maybe it would have been 77 or something like that. All right. That's an example of using this recurrent layers and this embedding, build a neural net for any language. Okay, maybe let's not dive into that. This is a net model that is good to tokenize any language because it doesn't use words, it uses subwords. By the way, we try to explain pretty well in this product page, you know, kind of the story of why this is useful and so on. So I encourage you to read, you know, in English, it's often efficient to tokenize text into words as the first step, blah, blah, blah. But in other language, words are not well defined. And that's why we use this by-pair encoding subword tokenization. And there are actually now networks that can take any language as input, like the same network, take any language as input. Like BERT has one version that is multilingual, and that we don't have yet. Unfortunately, we're working hard to put that into the net model, because that could mean that you train something in English and it could kind of work in other languages as well. It's not always the case, but still, it's kind of for free. You have your thing working in other language. So hopefully we can do that for text cases and question answering, find textual answer, and so on. So anyway, all right, an example of tokenization that is done in various languages with this BP encoding. Okay, that's an application about fitting missing words. So basically, this is using a language model that we trained ourselves. So it's in sequence predict. It's a built-in language model, and you can do that to kind of predict what is a missing word, but not just the word in the future, kind of the word in the middle. So what is the example? The example is the cat on the mat. So we have to find what's in the middle. And okay, jump, is, was, sits, and you do a little bit of simple things, and you can figure out that is the most likely word, was is seconds, that's somewhat less, and so on. And if you try the candidate avocado, it's pretty low, or the candidate, whatever you pronounce this, is even lower. That's a language model that tells us so. Okay. Autocomplete programs, so pretty similar here, using a language model but trained on programs, and can help you program. Generate Pokemon names. So basically, you take a bunch of Pokemons, and here you train from scratch language model, so that will model this new language, which are these Pokemon names, and then you can generate names. So let's see, that are fake Pokemon, but that sounds like Pokemon. So you can look at this example, and this one that generate bird names. So actually pretty similar. Let's not go on it. Okay, that's actually something else I wanted to mention that I realize is not in this page. It's the transformers. So let's see. Let's talk a little bit about transformer, and it's in the neural network page. We should have duplicated it. So yeah, transformer. So as I was saying, this new architecture, that is somewhat, new. Yeah, actually, that's a paper. Attention is all you need. The first paper that introduced it, that is, when was that? 2017, okay. End of 2017, since it's NIPS. So yeah, it's not that old. Yeah, 2 years old. And what it is, it's a self-attention system. So let me explain exactly. Let's look at that. So this is how you could think of processing text. So first, you pre-process each word and you extract a vector. Okay, that's an embedding layer. So you have vector for cat, vector for sat. All right. And so all of them is the same idea, right? You have one vector for each word, and then you pre-process. You still have one vector for each word. Although at some point doesn't really mean that this vector is associated to a word, but anyway. you always have a sequence of vector of the same length of the sequence of vector input, and you can do many times. So you can do convolution, then you can apply again and apply it another time and apply it another time. So you can put many layers of that. So okay, what a convolution would do on text, it's not a more classic thing. Okay, let's start with recurrence. That's a more classic thing to do on text. Is you read in the vector and you compute some state that you feed it to the next computation, when you read again the vector for cats, and then you compute the next stuff, and you read again for sat, and you compute the next stuff. And of course, actually, there's one arrow here, but there should be one arrow there because it's outputting the result of the computation in the middle. And that's how you process, right? So you try to keep in memory what happened in the beginning of a sentence in order to make sense of what happened in the last of the sentence, in the end of the sentence. Convolution will basically do a local computation. So basically this one is a computation of the, cat, and sat, but that's it. It doesn't know on, doesn't know the, okay? And if you do many layers, then at some point you can kind of merge the information that was here and here and resolved, some ambiguity. Like, what did Matt really mean? Maybe the fact that there is cat strongly influence what Matt means. That cat, I don't think it's yeah, I guess so. Math can be used in, I'm not, English is not my native language, but that math. Is it the math of a boat, or anyway, whatever. So okay, that's two different ways. They have, so the problem with the convolution is that it might take many layers for information to flow from one part of the sequence to the other part of the sequence. Recurrence information flow directly, but sometimes it's hard for the neural network to know what it should remember or not from the beginning of the sentence to give it to the end of the sentence. So attention kind of solve this problem. Is that when you look at this graph, really what it does is that each word compute a similarity. It's not a similarity of the word, it's more similarity of the embedding. So with the other words, so the and cat would kind of compare each other and figure out if they and this way you can very, very quickly combine, let's say, of Matt and cat. I see a question. Oh no, 2 minutes left. Okay, yeah, we're gonna wrap up. Very quickly, you combine in part of the network, and it's working much better. Okay, let's not go into detail. We don't have time, but much better. Casual attention in the same way, but this time the future cannot talk to the past, and so you can create language model. This is an example that explains BERT and GPT, that are two things based on transformer. GPT-2 is very famous, and we have it recently. So GPT-2, let's see, we added it recently to our repository. It's a model that's very impressive text generation. So let's see what it looks like. And you know what? I'm just going to look the example in the repository. So if I find GPT-2 here, GPT-2, here you go. So it's a transformer, and so problem of transformer is that it's pretty slow to run. That's a problem. Actually, yeah, if you figure out, sorry to get back to this, but yeah, because everything has to talk to each other, it's basically, it will scale like the length of the sequence square for computing the next step, while this thing is linear in the length of sequence, and this thing is linear as well. So that's kind of the drawback, but it give better result. And all right, let's see text generation, for example. Do we have a nice text? Albert Einstein was German-born theoretical physicist. who was born in 1985 in the city of Berlin. We don't know if it's true or not, but that's what the language model generates. He was a member of the German Academy of Science and the German Academy of Science. Okay, well, that's a bit stupid to say that twice, but whatever. Okay, it seems to be stuck to say it was in German Academy of Science. In 1985, Etienne was appointed to the post of Professor of Physics of the University of Vienna. He was a member of German Academy of Science. And okay. It seems, I think we put a too low temperature here, huh? Oh, actually, yes, that's an example of very low temperature. Okay, maybe you should read that one instead. Oh no, that's a high temperature. Maybe we should read the normal temperature. Anyway, here you go. Leaks induced identification, blah, 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 after uranium research status for, okay, so yeah, someone a little bit more diverse at least. But still, if you read it fast, often what this thing does, if you read it fast, you can't see that it's a machine that generated the text. If you read slowly, you can see some inconsistency. But it's much, much better than what was before. Like this all transformer plus training on big data set is doing a tiny revolution in NLP. I mean, at least a big progress. And this basically happened this year. So we're excited to see, and I guess that will be a conclusion. We haven't extracted, let's say, all the juice of all these new things. So we're excited to see how good the application, like how good text cases can be using these powerful transformers, and all the application we can do with that. And so I encourage you to try doing your applications yourself. All right, I think that's it for today. Thank you for your participation.